Robert Bau is a teacher and a mentor who made major contributions to the development of techniques for single crystal neutron diffraction. The Bau Award recognizes exceptional research achievement in neutron diffraction. The first Bau awardee is Dr. Tom Koetzle. Tom had an exceptional career in neutron diffraction and chemical crystallography. He played an important role in the development and support of neutron diffraction facilities at Brookhaven, Argonne, and Oak Ridge. For over 30 years, Tom collaborated with Bob and members of his research group from USC in a series of groundbreaking studies using neutron diffraction to study metal hydrides and related compounds. Tom also served as director of the PDB for 20 years. He published more than 200 research papers and mentored a number of postdocs who've gone on to have distinguished careers. It's my pleasure to present this award to Dr. Tom Koetzle.
Thank you so much, Cheryl, and thanks for everybody for being here. And it's a great pleasure, obviously, to be able to receive this award in honor of my dear friend and colleague, Bob Bau, and to be able to speak with you this morning. But again, thanks to everyone for showing up so early on a Sunday morning. And it's really an extraordinary and a humbling honor to receive this award from my friends and colleagues at ACA. So this is an attempt to summarize nearly 40 years of work, so bear with me if things go by too quickly. So 4 decades of single crystal neutron diffraction, and okay, so this is a picture of the high flux beam reactor at Brookhaven National Laboratory in New York, where much of this work was done. Now, neutron diffraction, neutron crystallography is going to have quite a presence at this meeting, but it is a special technique. And I'd just like to ask initially for a show of hands, how many people in the room have actually participated in a neutron diffraction experiment? So we drew a good fraction, but it's still a specialized and somewhat niche technique, as you'll discover if you, for example, look at the Cambridge database, where surely considerably less than 1% of the structures, way less than 1% of the structures, use neutrons, or for that matter, grounds a recent issue of ACA. So I'll try to start from the beginning, and those of you who are experts, bear with me. So this was the equipment inside the dome of the high flux beam reactor in 1976, and our 2 diffractometers, and the picture of Dr. Ray Teller, who is in the audience, and will be chairing the session tomorrow afternoon. I wanted to mention at the top that there's a session 1001, interplay of crystallography, NMR, and theoretical methods, which has been organized by Alberto Albanati and Larry Faldello, and there'll be a number of talks in that meeting, in that session that I'll refer to later on in my talk. Some 10 years later, things look much the same. The main improvement in those 10 years until 1985 was that we installed closed cycle helium refrigeration technology and started to do most of our work at low temperature. Now these are old-fashioned monochromatic beam point detector instruments. So this is the point detector. So they're much like the first generation X-ray diffractometers that many of us who've been around for many years remember from our early days. And we proceeded with collecting 1 reflection at a time, and on this sort of equipment it typically took us from maybe 4 days to 3 weeks to collect the data for one of our structures. Following the shutdown of the HFBR in the 90s, the management at IPNS, Ray Teller and his predecessor as IPNS director, Bruce Brown, and Art Schultz encouraged me to come to Argonne, and so I began to work on the single crystal diffractometer, the SCD instrument at Argonne, at the intense pulse neutron source. And this was really the prototype for many of the modern machines that are in use today, or a prototype for them. You see two area detectors here. This is a time-of-flight Lowry machine with a polychromatic neutron beam. And of course, all modern diffractometers use area detectors. This is a slide that I adapted from George Bacon's book on neutron diffraction. Professor Bacon was one of the real pioneers in England at Harwell of neutron diffraction. And this book became a sort of Bible for most of us when we were studying. And it shows the scattering amplitude. Nowadays we use femtometers for this unit, but at that time we were using 10 to the minus 12 centimeters. And you see the scattering power for X-rays, which I placed on the scale by multiplying by the classical radius of the electron, and the scattering factors for the scattering amplitudes rather for the neutrons. And right off the bat we see one thing, which I think most of us know. X-rays obviously have a form factor, and neutrons have one kind of arbitrary looking line here, or curve, or scatter, and neutrons are actually scattered as point scatterers. And of course this goes back to Rutherford's experiment from 1911, and to the fact that the nucleus is 10,000 times smaller than the length scale we're using in molecular structure, and the length scale of the electron distribution. And the other thing is, because it's a nuclear process, neutron scattering obviously depends on the isotope. So here we have hydrogen at minus 0.3 and deuterium at plus 0.7 roughly on this scale. So we gain several things with neutrons. Most importantly, from the point of view of a chemist, it's the ability to locate hydrogen, which we'll be showing in the talk. Secondarily, the ability to detect isotopes. And perhaps less obviously, the lack of a form factor means that generally you can carry out the experiment to higher resolution, particularly if you reduce the temperature and therefore gain more precision, and since you're locating the nucleus, a more accurate representation of thermal motion. There are two aspects that are totally missing from this slide. One, the neutron has a magnetic moment, and so it can be used to study magnetic structures, which Professor Javier Campo will discuss that application on Monday afternoon in that session. The other that I will speak about briefly, but will also be mentioned on Monday afternoon, is the neutrons of wavelength 1 angstrom have thermal energies. That means they can be used for diffraction and for spectroscopy as well as diffraction. And I know that people will be talking about that on Monday afternoon. So here's one application, which involved Hannah Yuan from Bob Bau's group, and their idea was to deuterate one of the positions on a methylene group, in this case an enzymatic product from having to do with alcohol dehydrogenase, and determine the absolute configuration of this chiral alcohol, which clearly is only chiral because it has a deuterium with that carbon. So this was one application that Bob and his students developed. It's very interesting. Now, how many people were present at Salt Lake City in 1997? Some people, at least. So those of us who were there will remember a certain performance by Professor Bau after the banquet. And Hannah actually is a professor in Taiwan now, but I have it on a good account that Hannah prepped Bob for his famous karaoke performance at the banquet. So he was able to wow us because he had a tutor. And that was Hannah who determined a number of these chiral alcohol structures. This is an example just to highlight what you can do with thermal motion. This is a study by my late colleague Dick McMullen and Oka Kvik on the so-called type 2 gas hydrate, and this is a mixed hydrate of xenon and carbon tetrachloride that Dick was actually able to crystallize. That was kind of a tour de force to grow these large crystals of this clathrate. And here you see the carbon tetrachloride in the large, what Dick called a hexachi decahedron 16-hedron cage. And it's quite disordered, so Dick was actually able to expand the delocalized chlorine density on the surface of the sphere using spherical harmonics here out to the 16th order, I believe. And it gives you an idea. You see the one chlorine atom here and 3 others in the back or front, as you prefer, and some delocalized density, which of course reflects the detailed potential inside that cage. And in turn, this is very important for the thermodynamic stability of this mixed clathrate, which also shows the facility of clathrates for gas separation. So we have xenon in the small cage and carbon tetrachloride in the large cage in this system. Well, Dick was, a mentor to many of Bob's students, an inspiration to all of us at Brookhaven, and I think those of us who knew him still remember him very well. His Dick at his retirement symposium, the Pittsburgh Diffraction Conference in 1994 with Alberto Albanati on the left. And I'm having difficulty identifying the gentleman on the right. If anyone knows, we can speak about that later. But, I owe Dick an enormous debt of gratitude, really, for all the work that was accomplished at Brookhaven. Well, one aspect of neutrons that's kept to the specialized technique of instant chemical crystallography is the need, at least until recently, for very large crystals. And this has largely been addressed, as Gary McIntyre will tell us tomorrow afternoon, with the modern instruments of both reactors and spallation neutron sources. But here you see a typical crystal that we would have used at IPNS, photographed by Paula Piccoli, who was our postdoc, with Art Schultz at IPNS. And you see that this crystal must be at least 25 cubic millimeters, depending on how thick it is in volume. So there was a joke going around in the chemical community: send your crystals to Tom and he'll tell you they're too small. So that was our problem. And as I say, the crystal is very, very large. Obviously, not every metal hydride, for example, could be induced to grow a crystal this size. So we like to paint these very pretty stories about what we did, but in truth, we have to admit that we studied mainly what we could get our hands on at many points in the story. Okay, so now I'm going to take myself back to 1970. In 1970, I arrived at Brookhaven as a fresh postdoc and to work with Walter Hamilton, who of course was a pioneer in crystallography, really among the second generation of neutron diffraction people. Neutron diffraction clearly goes back to Oak Ridge from, shortly after the war anyway, when Cliff Schell carried out the first diffraction experiments, and for which of course he shared the Nobel Prize in Physics. I see Gene Ice here in the first row, so we have Omar and El very well represented, and a number of other people in the audience as well. So Walter had written an article called The Revolution in Crystallography that appeared in Science a year or two before I arrived at Brookhaven. And basically what he was saying was, now we have all these wonderful diffractometers and it's a brand new world. So he was really also a president of the ACA and one of the leaders of our community, and was kind enough to take me on as his postdoc in 1970. And one of the things Walter was interested in at that time was using this technology to systematically study the crystal structures of the amino acids. And this is our first paper in JAX. We were young. We gave it this very pompous title. There were approximately 20 papers or so in this series, I believe. And Mogens Lehmann had joined our group, who subsequently went on to play a leading role in the development of neutron diffraction at the ILL in Grenoble. And together with some other collaborators, we set out to study. We thought we were going to study all the amino acids, but we couldn't crystallize all of them, and some things intervened. But we did study most of them, and I see that this slide is totally useless. Sorry, I thought I checked everything, but anyway, this is supposed, it does have enough bonds to let you know this is the NH3 group over here, and this is this carboxylate group over here, so they're all Zwitter ions. And of course they have strong hydrogen bonds. There are 5 hydrogen bonds, I think, in this, 3 hydrogen bonds in the structure, and they're strong. And there was an enormous amount of detail in these papers. That's one thing you notice. I went back and reread these papers from 43 years ago, and it was 42 years ago, and it was quite remarkable to see all these things that I'd totally forgotten, but there was an enormous amount of detail. And we studied the thermal motion in detail, and here's the methyl group, and here's the ammonium group, and you can see the hydrogen thermal ellipsoid, so it was possible to study that in detail and to apply the TLS model to get a vibrational amplitude, and from that, of course, the barrier to hindered rotation. And what does it say here? It says, well, the average length of the CH bonds in the methyl group is 1.096 plus or minus 0.003 of an angstrom. For whatever reason, that's identical to 4 places to what was in the tables at the time. I mean, that's pure luck, but anyway, it was quite precise, done at room temperature. And the barriers to rotation of the methyl and ammonium group are estimated to be around 5.6 for the methyl group and 20 kilocalories per mole for the ammonium group. Was that of any usefulness? Well, I mean, I kind of like to wave my hand. So if I divide this by 3, I get 14 over 3 is the contribution of 1 hydrogen bond, which is a few kilocalories, right? So this is a demonstration from this study that hydrogen bonds are a few percent the strength of chemical bonds, which of course is what makes them very interesting for biology, because they're on the order of thermal energies and they can rearrange quite easily, and they're very flexible, which we all know. But I thought it was amusing when I started looking at this paper that, I didn't say that in this paper, of course, because I was too concerned with the details, but anyway, it's interesting what you can get out of such a study in terms of basic knowledge. Of course, this was all well known at the time, obviously. In fact, Walter Hamilton had written this definitive text called Hydrogen Bonding in Solids with Jim Ivers in the 60s. So that was his motivation primarily, I think, for embarking on this series of studies. Well, one of the other studies in the series, we were lucky actually, we got accepted as a letter to Nature. And this is L-proline monohydrate, and it says direct methods in neutron crystallography. So we managed to solve the structure by Multan. And Jacques Verbist, who went on to be a professor in Namur, had worked with Gabriel Germain, or at least in the same department in Louvain. He was very interested when he joined our group at Brookhaven in applying Multan to a neutron structure. And of course it was thought that it would be difficult to solve such a structure simply because direct methods assumes that the electron density is always positive, which it is not for scattering density. Clearly is negative if we have hydrogen atoms in this structure, which we did. In fact, I think the scattering density is roughly a third negative, roughly. I'm not sure exactly. It probably says in that paper, but it's roughly of that order. And we just, of course, we were young. We just pretended everything was okay, and we went ahead and it worked. So we managed to publish this paper. But it has a very interesting statement in it. It says, we report here the first solution of a complex acentric organic crystal structure from the application of direct methods to neutron diffraction data. What's interesting about that? This is a complex acentric organic structure. That's 40 years ago, right? How many atoms are there? I don't know, I didn't count them, but certainly less than 20. Even with the water molecule. So we have indeed come a long way, but if you examine these papers, besides the printed structure vector tables, which look very quaint, there is a kernel of truth for us to remember, which is that, of course, we struggled for months to do each of these structures, so we paid a lot of attention to how we thought about the results. And there was a lot of information there, which of course you can't get out of many contemporary publications. While we were doing this work, we became aware that Professor Chidambaram's group in Bombay was working on amino acid structures simultaneously. This was a very different world, so we had no idea what they were doing. It wasn't quite like Rutherford, where it would take 6 months to find out what was going on in New Zealand. But I mean, we still had no idea what they were doing in India, no clue whatsoever in 1971. And L-asparagine monohydrate was just happened to be one of our structures that both groups did. So there's a paper from the group in Bombay, which was working on the Cirrus reactor, and our group from Brookhaven, same 4 characters here. And we thought that it would be a good idea to systematically compare these structures. They both look very good. So we applied Sidney Abraham's method of half-normal probability plots, and we have here the positional parameters on the right and the thermal parameters on the left. And we get nice straight lines. And the slope is a little different than 1. So from this we conclude that indeed these two structures, done completely independently, it's sort of a double-blind study in the sense we weren't even aware of that we were doing this. So neither of us did it with a view towards comparing it with anybody else. It certainly wasn't a so-called comparison round study where everyone is on their best behavior from the beginning. We just kind of blundered into this. And yet we conclude essentially no systematic errors, and because of from the slopes, we conclude that we underestimated the ESDs by about 1.3, which is kind of a rule of thumb that people had been using for decades anyway, because we all recognize that our ESDs tended to be too small. We could certainly discuss for hours why that might be so, but I think it was generally accepted that they were indeed too small. So this was 1972, and here's Walter. I couldn't, get through this talk without showing his picture. This is Helen Berman. This is a photo that my wife Carol, who's in the audience, took of us as we were crossing the North Sea on our way to a famous NATO summer school. It was, I think, one of the high events of many of our lives. I know there were a few people, Alberto Albinati amongst others, who were here who were actually at this meeting. And really, we had a great time there for 2 weeks, being instructed by the likes of Bob Diamond and various other luminaries, Carol Johnson, I think, and many other people. This was the period when Helen and Walter, together with Edgar Meyer, were dreaming and planning for the protein data bank. So there were a lot of things that started in those days. I want to spend about 5 minutes telling you about another project that I don't think is well known today, but Walter had the idea that we should look into the possibility of using neutron anomalous scattering as a structure solution technique. And this, I remind you, precedes bad phasing and synchrotrons by some years. And this was the period when Benno Schönborn had started to collect data on myoglobin at the Brookhaven high flux reactor, so people were thinking about and doing experiments. Sax Mason was working with Dorothy Hodgkin, who was looking at insulin in England, and people were starting to look at using neutrons in biology, which of course is a very big subject today. And we knew that we could use, in principle, this multi-wavelength technique, 3-wavelength technique, to solve our phases. So we embarked on a study of this EDTA salt, samarium, as a test case. And samarium is one of a very small number of nuclides that have strong thermal absorption resonances, strong neutron capture, high cross-section neutron capture reactions in the thermal region. And these resonances are very, very strong. And they produce enormous, by X-ray standards, enormous anomalous scattering effects. Now I've gone over to the more modern scale, the 10 to the minus 15th femtometers. At 1 angstrom, minus 21 plus 56i. What does that mean? A nitrogen atom, which is typically the largest scatterer in any structure of this type, has a value of 9.6 on this scale, or 9.6. So the imaginary part is 6 times larger than the scattering from any atom in your structure, which is huge. And so the idea was that one could use this to solve very large structures in principle. This is the samarium EDTA complex, so it has the usual class-rated EDTA, and it's got a unusual EDTA. It wraps around the samarium, 4 oxygens, 2 nitrogens, 3 water molecules, 9 bonds to the samarium. There are 5 waters plus a sodium completing the crystal structure. So it's a pretty complicated structure, at least from our standards from 1970. And it does have disordered water, so it's not a bad model for a structure you might wish to study. These structures had actually worked out by Young Cook Lee and Lynn Ward's group at Cornell in the 60s. And you can draw a lot of interesting conclusions about the structural chemistry from the size of the ions and so forth, but I'm going to skip that today. But it is a 9-coordinate ion. And what we did with Dennis Engel from Durban in South Africa, who joined our group to work on this. Dennis was a student of Walter Hoppe's in Germany, and had a deep background in anomalous scattering. He knew all about the theory, which goes back, well, a lot of it was developed in India by Professor Ramaseshan, Kartha. We know the names. So we chose 3 wavelengths, 2 on the long wavelength side and 1 on the short wavelength side of the resonance, which is at 0.92 angstroms. We're using naturally occurring samarium, which I believe is around 15% samarium 149. I have the exact figure there, which I have to look up, but it's of that order. And of course, we're applying exactly the same kind of theory, the same technique that's used today in mad phasing. So there are the 3 wavelengths we used. And these are the refined scattering lengths. So we refined all the scattering lengths and fit the theoretical Bright-Wigner curve from nuclear physics to it, and it agrees quite well. And of course, we chose 2 wavelengths so that the real part would be the same and the imaginary part would be different, and the other 2, the imaginary part is the same and the real part is different. And I don't want to show Argand diagrams today, but just remind you that from 1 wavelength we can only determine the sign of this angle, which is the angle between the structure factor and the real part of the anomalous scatterer contribution. And we can't determine the cosine, and we knock that problem out by introducing the 3rd wavelength. This assumes that we know the position of the anomalous scatterer, so we know the amplitude and phase of FA, which is the real part of the anomalous scattering from the heavy atom that would be in your parlance, or the more common parlance. And with this method, of course, we break the ambiguity and we can calculate the phases exactly for the eccentric zones, and we can determine the structure. And if we take the difference between the 2nd and 3rd wavelengths, which differ only by the imaginary part, of course we get a 1-atom Patterson. And here we see the Harker section is equal to 1/4, and we see the samarium peaks. We can use these coefficients to refine the positions of the heavy atom directly, and then we can use the other wavelength, λ1, which is on the other side of the absorption resonance, to determine the phases. And I know these are a little faint, but this is 1-methylene group through the EDTA. And the anomalous phases, just calculated, the map calculated from the raw phases, shows all the hydrogen atoms very well at 2 angstrom resolution. And here are the refined phases, and unfortunately I didn't quite manage to jack this up enough so that you could see it too well, but there's a 14-degree RMS difference between the raw and refined phases. So the structure solution method works extremely well. It never became practical. Why? Because very large crystals were required, and the absorption was incredibly high because of the large imaginary term and the strong resonance. But in principle, in this kind of structure, there's one samarium at about 67 atoms, I think I remember correctly. Some of the Bau differences were 50% or more. Many of them were. So you could determine a structure with hundreds, I don't know how many kilodaltons. I think we may have carried out a calculation, but a very large structure, because it's a very large effect. But I don't believe that it ever became of any practical significance, although Bartonek and his colleagues did explore it with cadmium myoglobin, cadmium insulin, I think, in Europe. And there was a lot of work done in the 70s, and in a way you could say it was the preparatory work in a way for mad phasing, but it still remained a curiosity. But it was a very interesting study, occupied us off and on for 15 years, so I wanted to tell everyone about it because I've almost forgotten about it myself. And this is the front piece from the book that appeared from the anomalous scattering meeting in Madrid in 1974 that was held at the Academy of Sciences in Madrid, that was organized by Professor Ramesatian and Sidney Abrahams. And this is a photo that Virginia has put in the archives of the people at this meeting. And you can see some very famous people here. There's Dorothy Hodgkin and Professor Nussbauer in the front row. This probably is Professor Ramesatian, I guess. This, I think, is Professor Perelman from Utrecht. I remember Professor Bijbo was too ill to attend this meeting, but Professor Perelman attended in his place. Mons Lehmann. And right here, Dennis Engel, who did the work on samarium with us. And you can see me lurking somewhere in there, but I'm going to refrain from pointing myself out continuously here. One person who was not there was Walter, who had tragically died in January 1973, and we dedicated this plaque in our Hamilton seminar room in the chemistry department at Brookhaven in Walter's memory, and it says, "In memory of Walter Hamilton and in recognition of his contributions to chemistry in 1973. It was a great loss for us and for crystallography and for the world. Now, Walter had done many things. One thing he did with Alan Davison from MIT and Sam LaPlaca was to determine the structure of the first molecular transition metal hydride, H-manganese CO5, in the late 60s. And at that time, people were debating whether hydrogen was a stereochemically active ligand, whether it had a normal bond length, whether it actually took up space around the metal. So very, very basic questions were being addressed. And Bau had actually approached Walter in late 1972 about starting this project on metal hydrides. So the work actually fell to me, which was a great good fortune for me. And I had known Bob from our days as students at Harvard, but I guess you could say this became the defining professional relationship of my life. So anyway, this is a structure that Ray Stevens did in 1989. It shows 6 phase bridging hydrides and a octahedral cluster of copper. So it's one possible interaction mode. And here the scientific question was whether or not these hydrides are symmetrically coordinated to these faces of the octahedron. This is actually our first paper from this collaboration, which Gerald mentioned in the introduction. And paper from Jax on HW2CO9NO. So this is what we call a binuclear hydride with a bridging hydrogen ligand. And what does the structure look like? I didn't have a convenient picture of that structure. So I'm showing HW2CO10 here. So the carbonyl is this is isoelectronic with the HW2CO9NO, because the carbonyl has one more electron than the nitroCl. So this one is an anion. And we have the bridging hydride, which looks symmetric here. And we say evidence for a closed three-center metal-hydrogen-metal bond. So we're inferring from the projection of the axial direction that goes to the center of the triangle that, in fact, we have significant metal-metal overlap here. And obviously, we couldn't do a useful calculation on this tungsten complex in 1974. But it's well known that there is significant metal-metal overlap in these systems. So this is what we call classical hydrides, which simply means we do have a discrete hydride ligand, which is a stereochemically active ligand. And these are 5 structures, 5 possible modes. This is an iridium structure with 5 hydrogen ligands in a plane. So it's a pentagonal pyramid, which was done by Saeed Khan, who's in the audience. This is the structure I just showed, HW2CO10-. This is a binuclear rhenium system with 4 bridging hydrides, which we called AGNOR at the time because we didn't know how many hydrides there were before we did the study that Ray Teller worked out when he was a graduate student. And this name AGNOR reminds me to emphasize that you really, at least at this point, certainly didn't know where the hydrogen atoms were in quite a few of these compounds when we started working on them. Of course, why? Because we had heavy metals here, we didn't have hardly any contribution to the X-ray scattering for the hydrogen atoms. This is another face-bridging hydride, sort of analogous to the copper-6 that I showed you on the previous slide. This has 3 hydrogen atoms bridging the 3 of the 4 faces of a tetrahedron of nickel. And lower right is the octahedral interstitial H-cobalt-6 CO15-. It's probably not the right number of carbonyls, sorry. CO24- maybe. So early on, we were focusing a lot of attention on binuclear systems with bridging hydrides, and this continued to be an interest for a long time. This is a structure that Alberto Albanati worked out with crystals that were supplied from the Benanzi group in ETH in Zurich. And here we've chosen the more traditional chemist view of the molecule, where we acknowledge that there's some interaction here, but we didn't draw a metal-metal bond. And this one has a phenyl group here and a hydrogen atom here. And we see the direct manifestation in this asymmetry, which is observed to about 7 or 8 standard deviations. We see the manifestation of the trans effect, of the trans influence, rather, of the terminal hydride HT, which causes that bond to be asymmetric, in contrast to what we saw in, for example, a symmetric complex like HW2CO10-. And when I was a graduate student, people were always saying, particularly in biology, why are you studying crystals? I mean, what does this have to do with anything that's actually important in the world? Because everything goes on in the solution. Well, in chemistry too, there's a relationship between the molecular structure and the solution chemistry. And here, when we cleave this by reacting with a halide anion, we get the cleavage trans to the hydride, which is what you expect. That's the weaker bond because of the trans influence. So the crystal structure is reflecting the solution chemistry. I mentioned that we often don't know what these compounds look like. This appeared on the cover of Angewandte Chemie, and it has this statement. The 2 cones, so this is a ferrocene-like structure, except with cobalt. The 2 cones are linked by a double bond. They give the length, and they say it's stable without any bridging ligands. And they say that there's 16 valence electron configuration to the cobalts, which is usually not favored. And actually, this structure was carried out at Brookhaven. And one of my postdocs, Ping Wu, was involved with this together with Bob's students, and it actually has 3 bridging hydrides. So it's not a very good model for a ferrocene. And it's paramagnetic because we've added 3 electrons. So they should have presumably had some idea that it was paramagnetic before we collected neutron data, but that was the facts of life. So often we were actually doing a very expensive form of analytical chemistry here. This is the octahedral interstitial I mentioned before. It is H cobalt 6 CO15 minus. Again, done by Don Hart, who was one of Bob's students. And at that time, there were several other equivalent octahedral interstitial hydrides, a nickel 12 from Larry Dahl's group, and I think it was a ruthenium 6 complex from the Jack Lewis's group that Paul Wraithby was involved in, I believe. But it was a big deal because you could put a hydrogen inside a cluster and it actually expanded about, I think, 7% in volume, which of course is an analog for hydrogen-induced strain and embrittlement in metals. You could have a reverse situation, 6 hydrogens around an iron, which we did with a group from British Columbia, Sidney Gibbons, and it was actually made into a stamp by the Canadian government from the Canadian Chemical Conference. So it's a good thing to say at the ACA where we always emphasize our Canadian participation in the Canadian division of the ACA. This is the rhodium-13 cluster. It was basically the last structure we were able to do at Brookhaven before the reactor shut down. It has 5 coordinate hydrogen atoms. And here's the core. You can see there's a hydrogen here, and it's coordinated to 5 rhodiums. And here are the 2 hydrogens on the faces. So those were the first 5 coordinate hydrogen atoms. This structure, which I think has 127 atoms, required 3 months of data collection on the Brookhaven reactor because the crystal was very small. Luigi Galliskelly had obtained the crystal in Milan. It was quite a tour de force. We tried to work on the structure for 10 years or more. But Professor Albano in Milan, who had originally determined the X-ray structure in the 70s, was very pleased when I was able to tell him the hydrogens were actually where he thought they were. Now Bob, yeah, I know, just give me about 5 minutes. Bob was very astute at drawing conclusions here, and he published a lot of the papers that gave correlations, but you see how the bond distances increase with coordination number for these rhodium compounds. Mohammed Yusufuddin, who's in the audience, subsequently produced a tetrahedral interstitial hydride structure with this Neutron compound, which was also, Bob said it was his holy grail, basically, the tetrahedral interstitial cluster. I just want to finish up by mentioning that there was a lot of work on beta-2 dihydrogen complexes, which are so-called non-classical hydrides. Craig Jensen had worked a lot in this area, is in the audience from the University of Hawaii at Manoa. And the basic idea is you take a hydrogen molecule, you stick it side on in the metal, and you lengthen the HH bond, and it's a model for hydrogen activation. The basic model for this is sigma donation from the dihydrogen to the metal and pi back donation from the metal to the dihydrogen, which of course weakens the bond and causes it to have a barrier. These compounds were made first by Greg Kubas at Los Alamos. This is called Kubas's compound, this tungsten system. And you have a hindered rotor here because of the back donation. And because it's so light, the hydrogen, you have a quantum mechanical rotor. This is a freshman physics kind of demonstration. You have a splitting because of tunneling, and you can do the spectroscopy on that. So it's called tunneling spectroscopy or proton tunneling. This is a ruthenium complex, again with an H2, made by Bob Morris, that Alberto and others determined the structure. So it's octahedral, 4 phosphorus ligands, a dihydrogen and a hydride. And you can do this inelastic neutron scattering experiment, which was done with Jürgen Eckert, and you can measure these wing lines, which are reflective of the splitting, which in this case is a little less than 4 wave numbers, which corresponds to a barrier around 1 kilocalorie. So that's much weaker, lower than the barrier in a hydrogen-bonded ammonium group, obviously, or a methyl group for that matter. These spectrum, when you see these subsidiary lines, is very diagnostic for the existence of this compound. You can see here we changed the metal and we exchanged one of the phosphorus ligands for a hydride. You see we get a very different spectrum. The barriers do tend to be around 1 kilocalories, which is why we get such smart tunneling. I don't have to finish in 1 minute, so I will. Subsequently, I moved to argon, as I mentioned, at the behest of Ray and his colleagues, and worked at the IPNS, which you see here. Many of us will recognize the IPNS here in the upper right. I mean the APS, the Advanced Photon Source. And we did many studies there, and I just show very briefly one on tetraacetyl-ethane, which is a short, strong hydrogen bond, about 2.45 angstroms, I believe, from oxygen to oxygen. Studied at 20 K at the IPNS. And of course, the trick was, what is happening to that hydrogen atom? Do we have a so-called resonance-assisted hydrogen bond, which would be totally symmetric, or do we have disordered keto-enol tautomers here? And we studied it at 4 temperatures, or I should say Paula Piccoli and Art's group did. And you can see that the hydrogen is becoming much more disordered at room temperature than it is at 40 K, which we would obviously expect. But if we plot the CO and OH distances, you can see they're converging. And the CO distances, in fact, so these two distances, C101 and C202, have become identical at room temperature. And the 2 OH distances are converging. And this is, quite ordinary. It's been seen in many compounds now. This is a difference map just showing the smeared out hydrogen density at room temperature. This is, of course, it's all mediated by the intermolecular contacts here. What else could be changing with temperature? So as the crystal shrinks, at low temperature, the bond is becoming more disordered. And this is very similar to a lot of work that Chick Wilson and his colleagues have done in England. I think Chick is here at the meeting, and he'll be talking about something related to that on Tuesday afternoon in the Transaction Symposium. We worked with Alan Pinkerton's lab, and Paula did a charge density, and you can see here's a charge density. So this is the OH covalent bond, and this is the hydrogen bond with a long pair. But the Laplacian really shows the covalent bond, and that was a very interesting study. It's one other application of neutrons, obviously. Here we see Art and Paula and our group at IPNS, and a group of people with Gordon Jones and Tom Gentile from Hamilton College and NIST, who are working with the group from Oak Ridge on helium filters for magnetic polarization. This is where neutron flux topped out when I started in 1970 with the most advanced reactors. This is Chadwick in 1932, so 15 orders of magnitude. But we couldn't go any further with neutrons from reactors, really, because of the thermal problem. And here are the spallation sources, and the new sources up here, which are another 2 orders of magnitude more intense. SNS, which came online in the early part of this decade, and J-Park in Japan, and the future European spallation source, which will come online later this decade. The team at Oak Ridge developed this instrument, Topaz, for single crystal diffraction. Bob was a guiding light for the instrument development team with many of the rest of us, and it's working now. Proposals the call is out. They'll be due at the end of this month. And you can work on both small and large molecules, pretty small crystals. Well, Gary's going to tell us that we've gone even further than that. Our dream, which is essentially realized today, is to work on X-ray sized crystals. You can do a lot of interesting things because you record. This is, again, a time-of-flight Lowry technique. You can record all of reciprocal space simultaneously on these area detectors. Look at diffuse scattering, phase transitions, magnetic peaks. fusing instrument at the SNS. And finally, JPARC, which has this diffractometer that's been working for several years now, IBIX, which stands for Ibaraki Prefecture Biological Crystal Diffractometer. You see all the area detectors. This is the hallmark of a modern machine. Many, many, many area detectors surrounding the whole sample. And they published this article in Science recently. Hydrides are still interesting. This is the model for the core of the hydrogenase structure. So as Dan Nocera told us last year at the banquet, metal hydrides are going to be very important for hydrogen production and utilization in the hydrogen economy. And I just want to show this slide, which is how I went to Bob, which is from the Geneva IUCR conference and was photographed by our friend and colleague Tom Mack from Hong Kong. Sorry for keeping you over by a couple of minutes, but thank you very much for your attention.